Hey everyone, welcome to my channel. If you like tech and helpful tips, don't forget to subscribe. Let's get started.
Deionizing water is a crucial process for countless applications, from laboratory experiments to electronics manufacturing, where even trace amounts of mineral ions can cause significant problems. Essentially, deionization, or DI, is the removal of dissolved mineral salts and other ionized particles from water, leaving behind ultrapure water. It's important to understand that deionization primarily targets ions, not necessarily non-ionic contaminants like bacteria, viruses, or suspended solids. For those, other purification methods like filtration or reverse osmosis are typically employed, often as a pre-treatment step to extend the life and efficiency of DI systems. The core technology behind deionizing water relies heavily on ion exchange resins, which are tiny, porous beads designed to capture specific ions and release others. There are two primary types of ion exchange resins used in deionization: cation exchange resins and anion exchange resins. Cation resins are typically charged with hydrogen ions, H+. As water flows through these resins, positive ions like calcium, Ca2+, magnesium, Mg2+, sodium, Na+, and potassium, K+, that are present in the incoming water are attracted to and bind with the resin beads. In exchange, the resin releases its hydrogen ions into the water. Following this, the water then passes through anion exchange resins. These resins are charged with hydroxyl ions, OH. As the water, now containing excess H+ ions and depleted of positive mineral ions, flows through the anion resin, negative ions such as chloride, Cl, sulfate, SO42, nitrate, NO3, and bicarbonate, HCO3, are attracted to and bind with the resin. In return, the anion resin releases its hydroxyl ions. The beauty of this two-step process is that the hydrogen ions released by the cation resin combine with the hydroxyl ions released by the anion resin to form pure water, H2O, effectively removing virtually all dissolved ionic impurities. For even higher purity, sometimes a mixed-bed resin system is used, where both cation and anion resins are intimately mixed in a single tank, allowing for multiple exchanges and extremely low conductivity water. Before water ever reaches the DI resins, proper pre-treatment is often essential. Sediment filters remove larger particles, and activated carbon filters are vital for removing chlorine, which can damage the delicate resin beads over time. Reverse osmosis, RO, is also a popular pre-treatment, as it removes a significant percentage of dissolved solids, greatly reducing the load on the DI resins and extending their lifespan, making the overall process more economical in the long run. Once the water passes through the DI system, continuous monitoring of its purity is crucial. This is typically done with a conductivity meter, as deionized water has extremely low electrical conductivity due to the absence of ions. As the resins become saturated with captured ions, their effectiveness diminishes, and the water's conductivity will start to rise, indicating that regeneration is needed. Regeneration is the process of chemically restoring the resins to their original H+ and OH states. Cation resins are regenerated by flushing them with a strong acid, like hydrochloric acid, HCl, or sulfuric acid, H2SO4, which strips the captured positive ions from the resin and replenishes it with H+ ions. Anion resins are regenerated using a strong base, typically sodium hydroxide, NaOH, which replaces the captured negative ions with OH ions. This regeneration process generates wastewater containing concentrated salts and acids/bases, which must be handled and disposed of responsibly, often requiring neutralization. For smaller, consumer-grade DI cartridges, regeneration is usually not practical or safe for the end user, so the cartridges are simply replaced when exhausted. Larger industrial systems, however, are designed for multiple regeneration cycles. Beyond traditional ion exchange, advanced methods like electrodeionization (EDI) exist, which combine ion exchange resins with ion-selective membranes and an electric field to continuously deionize water without the need for chemical regeneration, making it a more environmentally friendly and continuous process for very high-purity applications. Thank you for watching, and please consider subscribing for more insights into water treatment technologies.